Well, greetings everyone, and thank you for joining the ASBI monthly webinar here with us today. We have just a few announcements to make before we get to our presenter. I'm Greg Freeby, the Executive Director of the American Segmental Bridge Institute. I'd like to encourage you to follow me and the American Segmental Bridge Institute on LinkedIn. There you'll find not only information about the upcoming monthly webinars, but other activities that ASBI is doing, as well as some look back on some historical projects that the American Segmental Bridge Institute has been involved with, either through our awards program or other means. So again, encourage you to follow us both on LinkedIn. So some quick announcements. Just as a reminder, we are doing monthly webinars. They're traditionally the last Wednesday of each month from noon to 1 Central Time. Registration's open on the ASBI website at least 1 month in advance. Our June webinar is actually already available if you want to register for the June webinar. And then recordings of past webinars are also available on the ASBI website. Our June 28th webinar is about opportunities for launching gantries and precast segmental construction, led by Harry McElroy with McNary Bergeron. And again, that's on June 28th from noon to 1 Central, and registration is open on the ASBI website. We also have upcoming a construction practices seminar in New Orleans. This is at the Kempton Hotel Fontenot, which is located in the Central Business District. It's just a short walk from the hotel to the Bourbon Street and French Quarter areas. We'll be doing an evening reception hosted by the hotel each evening, an opportunity for folks to visit outside of the formal, I'll say, instruction or seminar itself. Room rate is a very low price, and that room rate is also available 3 days before or after the event. So if you want to sort of overlap the trip to New Orleans for some instruction with a trip for some recreation, then certainly that's available to you. Registration is open on the ASBI website. I would encourage everybody, regardless of your role, whether you're a contractor, a designer, an owner, a material supplier, everybody who would be, I'll say, touching any part of a segmental bridge would really benefit from attending this seminar. It's a great introduction to segmental bridges that goes even deeper, since it's basically a day-and-a-half seminar. You get a lot more information. We have opportunity to get a lot deeper into some of the topics surrounding around segmental bridging. So again, encourage everyone to attend the seminar in New Orleans. We also have upcoming in November our 2023 convention. It'll actually be our 35th annual convention. We'll also be hosting committee meetings. The committee meetings will be on Sunday, November 5th, and the early morning of November 6th. The conference itself, the convention, begins at 1 o'clock on the 6th. The technical program that'll run through noon on the 8th. ASBI is also hosting the bridge-related PTI committee meetings in the afternoon of May 8th and all day on May 9th. So if you're used to attending those with us, notice that's a little bit of a schedule change. We historically had been meeting on the weekend. The PTI meetings were on the Saturday, Sunday of the weekend, and we decided to give it a try this year to keep people at home a little more, not have to travel on the weekends or be away from home. So the PTI meetings then will be on the days after the ASBI convention. Just a reminder about our latest publication that's available. It's the Durability Survey for segmental bridges. This is an newly updated survey from our last one, which was published in 2012. We've expanded the data set to include additional known segmental bridges that we've identified. And it's all pulled from the National Bridge Inventory Database, which gives us some really great information about the condition of those segmental bridges. I'm happy to report segmental bridges are performing very well, and you'll find in the report we talk about that, and we even address the few that are currently in the database that are in poor condition, and we talk about why that is and what the circumstances are. So a good again, a great reference document if you want to know a little more about the durability of segmental bridges. So some instructions on the webinar, how it functions today. If you lose a connection, you can rejoin the webinar at any point. You will miss content while you're away, but you should be able to rejoin with the link you were provided. We will be offering certificates of attendance for professional development hours for those who attend the minimum required in the session. If you think, typically it's an hour we're looking for, we may run a little bit long. You're not required to stay beyond the top of the next hour, but certainly we encourage you to do so just to be part of the conversation. You will also, if you'll allow us a week to get you your certificate via email, that would be helpful. We have a process we have to go through to verify time and attendance. And then we'll also be doing Q&A at the end of the presentation, and I'll talk about how that works. Because we have so many attendees, we're not able to do Q&A verbally, so you have an opportunity, though, to ask questions at any time during the presentation. You should have a little questions pane in your little pull down in the GoToWebinar dialog that allows you to type in a question, and we'll hold those questions until the end of the session where we'll do a moderated Q&A. So if something comes up while the session's going, just go ahead and pop that into the questions pane, and we'll catalog those and then do a Q&A with our presenter. I keep jumping ahead. If you're on a mobile device, on an iPad or iPhone or some other mobile device, you should have a little question mark in the dialog that you can just tap on the little question mark, and it's the same thing in terms of being able to type in your question. We will be issuing certificates through the RCEP program. And this is the typical, I will say, disclaimer slide that we're required to provide that shows that we are meeting the RCEP requirements for issuing continuing ed certificates. I mentioned earlier that we'd be doing a moderated Q&A, and I will go ahead and introduce our Q&A moderator right now. Wade Bonzen with FIG Bridge Inspection will be our moderator. You can see on screen Wade's qualifications. I won't read all of them to you, but rest assured, Wade has a lot of experience in segmental bridge construction, so much so he now serves as the chair of ASBI's construction practices work group, and will be very instrumental in our upcoming seminar that we're hosting in New Orleans that I mentioned earlier. So then our speaker today is Mr. Jordan Session with Structural Technologies. Jordan's going to be talking to us today about a portion of his experience. He has over 10 years in the industry, working on a number of bridge projects, and I didn't even begin to list all of them here on screen for you. He's worked on a lot of projects, has a lot of areas of expertise, and holds a number of certifications also from ASBI as well as PTI and from VSL. So I'd like to welcome Jordan to present, and I'll go ahead and flip over to let Jordan share his screen, and he'll be able to then make the presentation. So Jordan, the floor is yours.
All right, thank you, Greg. Let me get this presentation started. All right, well, thank you for that introduction. So today we're going to be talking about a pilot project that we did on SH-146 in Kemah, Texas. This was a pilot project for electrically isolated tendons, also known as PL3 tendons. We'll get into some of that information there. This was a partnership with FHWA and TxDOT, and it was the second of 3 pilot projects that are going on in the United States to help identify if this is a type of technology that should be implemented in a more robust scenario moving forward. So the main idea, because it is a very new technology for use in the United States here, is we really want to understand what the difference is from a PL2 versus a PL3 tendon. And then the bulk of this presentation is going to be covering what is EIT. We also incorporated some additional technology that we call the void corrosion sensor. It goes hand in hand with what EIT is. And we're going to talk at first just kind of, what's the benefit? Why are we looking at these kind of technologies? What's kind of spurring this advancement? And at the end, we'll get into the details of our results for the pilot project, what that looked like, go through a lot of pictures of the project, and a couple of graphs and tables of our results. So advancing post-tensioning practices. So there's a big push, has been. We always want to improve what we're doing, right? We do this through the service life, the infrastructure service life, creating resilience in our structures, things like applying new and improved standards, better quality control, advancing with the times, right? Using modern and innovative equipment to do what we do better. There's been some resilience of using replaceable PT in a couple locations across the United States, and integrating intelligence, which is more of what the EIT allows us to do. So here's a real nice summary of just, here's all of the additional technology we put into this pilot project. Get my laser pointer here. So this is a series of straddle cantilever bent caps in Kemah, Texas. They're all post-tensioned with 4 tendons each. This is a cut section of the EIT tendon, where you can kind of see the innards of the isolation plates, the anchor, and how all that fits together. We have what we call the void corrosion sensors, VC sensor. This was a little mock-up testing that we did to kind of calibrate the sensor so we can get an idea of what results we're looking for. We routed, this does have wires that we need to connect to take our measurements. And we have a junction box where everything is routed to have a nice central location to take those measurements. And we additionally did vacuum assisted grouting on these EIT tendons. This was a way of eliminating the need for high point vents, which is a possible intrusion for electrical leaks. This also ensures a higher quality of grouting because there's additional testing that has to happen to make that successful. All right, so now we're going to talk about kind of the needs of what's spurring the innovation of this technology. Why do we need it? And it's really for corrosion of the strands. So post-tensioning has 2 different types of what we call attack scenarios. So the first one is an external attack scenario. We have the destruction of the passivation. That is, the passivation of the steel is how well it's able to withstand corrosion. We have straight currents from DC, high-speed rail and things like that can cause issues. Moisture inside the tendon or getting in from the outside is kind of an obvious one. There's risk for segmental construction in general for, if there's a lot of issues with post-tensioning tendons, that's going to affect the industry. And we have internal attack scenarios. So these internal ones are happening inside the tendon. And the 2 main ones we're going to talk about is unstable grout. This is grout that either has too much water content, has contamination that's in there. We've seen that happen throughout the history of post-tensioning of issues with the grout that comes up periodically. And we've advanced a lot to try and mitigate and eliminate those issues, right? We also have incomplete filling of ducts, presence of water, oxygen, voids in tendons. This is something that's really dictated by the quality control in the project of if we can eliminate this or not. So how do we identify PT corrosion in our existing bridges? So we know post-tensioning bridges has been around for many decades, right? We've had a lot of advancement over the years and we've solved a lot of problems, but we also have a lot of older structures that we need to keep an eye on, right? And even newer structures, sometimes we have issues with if there's quality control problems. But how do we identify the PT corrosion? Well, it's usually a reactive measure. It generally requires some means of destructive testing to really look inside the tendon and see what's happening. So more often than not, we're being reactive to it. We may see cracks in concrete, we might see a failure of external tendons, and that's when we know that there is problems with corrosion or something going on with our bridge. And at that point, there's already serious damage that's occurred. While we do have preemptive measures to identify it, it usually requires destructive testing. It can be very expensive because you don't know where you're looking at. You kind of have to hit, just look at everything in the bridge, which can be very costly, time consuming. And you don't know when it might occur. It might be good 10 years after construction, but at year 15, something happened and you may have to go back and check again. So it only gives you a point in time reference of what's happening on your bridge. So electrically isolated tendons, what is it? So we have a definition of protection level 1, 2, and 3. Just very briefly, we'll go through what each one of these are. So PL1 is going to be your basic post-tensioning tendon. It has minimal corrosion protection. It's your basic metal duct. You have grout. You have, of course, all your post-tensioning elements to it. But the encapsulation of that tendon is minimal. It's suitable for environments that have very low aggressive, very low exposure, places where you're just not going to expect a lot of corrosion to occur, and they can be suitable for those environments. PL2 tendons, which is really the main standard that you see across many DOTs today. This has increased corrosion protection using plastic ducts, permanent grout caps, engineered prepackaged grouts, things like that really help keep the moisture outside of the tendon and keep the strands protected. PL3 is what we're talking about when we say EITs. So PL3 not only has the corrosion protection that PL2 does, but it has active monitoring and protects it from stray currents. So that active monitoring is really what I would say sets it apart from PL2 and gives it a basis for having a wider application. So for anyone who's not too familiar with what PL2 is, or post-tension in general, here's a nice cut section showing the ducts, the strands, bearing plate, anchor head, wedges. And the main items that PL2 has for it is the plastic ducts, permanent grout caps, and then the engineered grout. So EIT tendons, they're defined. We define them with PTI ASBI M50. FIB 33 also has a definition for it as well. They're PL3s. The strands are electrically isolated from the elements outside the tendon envelope. So this plate right here is what we call the insulation plate, and it isolates the anchorage, the anchor head, from the bearing plate and creates that isolation that we're looking for. It also is required to be monitorable at any time, so that's not just during construction, but that's also going to be throughout the service life of the bridge itself. So the electrical isolation, we're not just concerned about stray currents getting to the tendons, but the isolation proves the water tightness and the prevention of contaminants throughout the lifespan of the tendon. So if water is able to get inside the tendon, say there's a break in the duct and water is traveling through the concrete through a crack inside the tendon, your tendon will lose isolation, electrical isolation, very quickly. And that will come up in the monitoring. So it's not just keeping electrical currents out, it's also proving that the tendon is still completely encapsulated. So a couple of benefits for EIT. The first is, of course, it has the full encapsulation, just like PL2. The straight currents is really essential when you have high-speed rail or other high current on your structure. And then the monitoring of the electrical isolation throughout the life of the tendon. So while PL2, we could say PL2 has those corrosion benefits, you're not testing every single tendon throughout the life. You're testing the system, you're making sure that the system is meeting the standards, but then when the installation occurs, you need to have sufficient quality control to make sure everything gets placed correctly. The EIT allows us to actually take measurements of every single tendon, so it's not just relying on the quality control to make sure it gets installed properly. We actually have results that we can look at, review, and determine if that isolation is being maintained throughout the life of the tendon, life of the structure. So here's an exploded view of that tendon. Most of these components, they're pretty much all the same with the exception of the insulation plate. That happens from between the anchor head and the bearing plate. Depending on the post-tensioning system, this trumpet may or may not be different. The grout cut may or may not be different. But it's essential that the trumpet is plastic and it extends from the face of the bearing plate to the duct. We want to make sure that the strand does not have any kind of metal-to-metal contact with the bearing plate, or obviously anything else outside the tendon, because that will cause loss of electrical isolation by making contact with the bearing plate. So what are we measuring? We're checking for isolation between the tendon itself, the strands inside the tendon, and the rebar cage inside the structure. We know if you ever looked at any kind of rebar cage, everything's tied together, everything's making metal-to-metal contact. So if we're able to isolate the strands, if we can take our measurement between the strands and any part of the rebar cage, we know that there's no metal-to-metal continuity going on anywhere. We also know that grout and concrete are electrically conductive. They have moisture inside them, especially when they are fresh grout. They're very conductive. So all of these can play a role in how our measurements are taken and what kind of results we're going to expect to see. So we use an LCR meter to check for the resistance between the tendon and the rebar, and we're looking for a very high resistance that indicates that it is well isolated. So here's two different diagrams showing the measurements and kind of the two different scenarios we might have. It is important to note that we make these measurements in 1 kilohertz in parallel mode. That is for that represents the characteristics of the tendon and allows us to kind of standardize what our results are. So in the ideal situation, we have the resistance of the grout, we have resistance of the concrete, and we have the duct, which acts as a break in that continuity. So we expect to see a very high resistance because there's no continuity between the grout and the concrete. If we have some kind of defect in the duct, maybe the duct had a break in it, or there's a kink in the duct, form tie penetrated the duct, whatever it might be, we've now bridged that gap and we have additional resistance in there, but it's something that we're going to be able to see in our measurements as far as what kind of resistance we see. So our measurements are, again, we're checking for isolation between from the strands and the rebar. It allows us to locate any defects. We'll get into that in just a second. We're able to measure it for not just during construction, but also for long-term service life of the bridge. All right, so here's a typical graph of what we would see for our measurements. On the y-axis, we have our resistance in ohms, and X is over time. So we start off immediately after grouting is going to be the lowest resistance that tendon has. The grout is still fresh, it's very wet. Wet grout is highly conductive, so it's going to have very low resistance. But as that grout cures, as it hardens, that resistance is going to increase. It's eventually going to hit a peak, and we expect it to stay at that level for the rest of its life. Kind of like concrete, it should gradually increase in resistance, but it's more or less going to stay the same. Now, if we're taking measurements, say periodically every year, and we notice that after a couple of years of it being at this nice high resistance, all of a sudden it drops off. That's an indication that something's happened in the structure. You know, if it's a segmental bridge, maybe it's a joint that's now opened up or cracking that's occurred that's allowed moisture to get in the tendon. But we know that something's happening that's caused the change in this resistance. And we're able to then go in, identify, go into that span that the tendon's in and try and identify what the problem is and address it. Now, it is important to note that just because it's lost resistance doesn't mean that the tendon has corrosion. It doesn't mean the tendon has failed by any means. It just means it's lost electrical isolation. So if we can catch this early and not wait 5-10 years for the corrosion to set in, we can address these problems before they become, we can address the issue before it becomes a problem, right? So there's a lot of benefit to being able to monitor these and being able to address them. So during the construction, we have a couple of control points that we want to check during the installation of these tendons. So the first one is checking for isolation between inside the ducts and the rebar. So we can do this with a pre-pour air test, right? If we can make our duct connections airtight, then they should be grout tight and eliminate any kind of intrusion that way. We want to check for isolation after we install the strands during the threading, and we also want to check it after the tensioning. The reason we do this is if there's some kind of kink in the duct, once you tension it, there's potential for the strand to slightly wear through the plastic, reducing the resistance that it's creating. We also want to check during the grouting and throughout the service life. So the typical expectation that you would see is a very high resistance after tensioning, and then once you grout, that resistance would actually lower temporarily and then steadily increase back to where it was. So what do we do if we have a leak, or if an electrical leak, I should say? The most common places that we're going to find a leak would be in any kind of connection. So anything that penetrates the duct, that could be a grout cap connection, trumpet duct connections, the grout vents. If there's any kind of penetration, say a post-grout inspection, those are all places where we most likely find a leak. If you're talking about segmental construction, you also have segment joints. That'd be a common place to find them. So this is a non-destructive method for finding a leak. Is what we can do is apply an AC source to the tendon and to our rebar and create a circuit, right? If we know that there's a leak, then we know that these are connected and it creates a circuit. That circuit's going to give off waves that we can detect from the surface of the concrete. So if we were to take our meter, run it over sector A, we're going to see this signal, right? And then as we cross from sector A to sector B, that signal is going to drop. And that's going to help us pinpoint exactly where that defect is at. So that could be, again, segmental construction. It could be a segment joint and find out, okay, this is the joint that's causing our leak, or maybe it's multiple joints, and go in and do some more thorough investigation. Instead of trying to look at every single joint on a bridge, we can really pinpoint this is the particular span or this is the particular joint that we're having a problem with and seal it up. So here's a very brief, just kind of EIT history on it. This is really kind of focusing on the UK, but you can see electrically isolated ground anchors were first used in 1992. So this kind of technology has been around for quite a while. It's been used generally in, as needed kind of scenario, but it's developed and there's been a lot of improvement since 1992, right? We've had the introduction of plastic ducts, and PTI and FIB7 around the 2000 area. We've had issues of internal PT being banned and then lifted because of problems that they've had with bridges. We've created a standard for EIT tendons all the way back in 2001. PTI and FIB had developed the protection levels that we use today, so PL1, 2, and 3. Created definitions for those so we have some kind of standard to measure against. And it's been used on a lot of projects throughout the years. So here's just kind of a very brief sample of some very major bridges. A lot of these are in Europe, Switzerland, but you see United Kingdom, Hong Kong, Czech Republic, So this is a technology that's been around for many years, used in a lot of bridge applications. By no means is this a fresh out of the box, new, untested technology. It's been through the rigors already. So the second piece of technology we added in here is void corrosion sensor. So going back to our attack scenarios, we talked about the external attack is the EIT helps us identify and mitigate the external attacks. It keeps everything, it helps us know if anything has entered into the tendon or can enter into the tendon. The void corrosion sensor allows us to see what's happening inside the tendon. So these are little probes that go into your grout vent connections. It doesn't allow grout to pass through. This would be an additional connection at the grout vent, but it goes inside the duct with your standard connections. It also can be attached at the anchorages and any other place along the tendon that you might want to take a look at. But these are typically put in locations such as high points and trumpets where you're going to expect the most common places for voids to occur. So the main objective of the void and corrosion sensor, it's got two. One is detecting voids and the second is detecting corrosion, right? So we want to check for voids, make sure the duct is completely filled with grout. We know it's supposed to be completely filled with grout, but it's really dependent on your installers, making sure that they are qualified and know how to do the work and the quality control is being implemented. So this gives us a measurement to say it's impossible to fake it. It gives you an actual measurement of is this tendon filled or is it not filled. It does this by having two different electrodes. So you have an inner wire electrode and then you have an outer ring electrode. And as it fills up with grout, that grout bridges these two electrodes and it creates a path for it, right? So we're able to then detect if it's full of grout, and we can even detect what is bridging that. Is it water? Is it a watery grout? Is it grout? All those kind of things can be determined based on what kind of results we see with this VC sensor. So here's a little bit of theory about how it's working. I'm not going to claim to be an expert in it, but I will pass on the information that I understand about it. So we know that there's different areas or different stages of what can cause steel to have corrosion. The grout creates a very, I should say, a well-mixed, well-designed grout creates a passivity on the steel that will really prevent corrosion. It creates a very strong resistance to it. And that's what the VC sensor is measuring when it's checking for potential for corrosion. So what it does is during the measurement, it applies a voltage to one of the electrodes and basically cleans off the inner wire by doing so. It then applies a voltage on the opposite electrode, creating a difference in potential voltage between the two. And we're checking for the passivation here. We want to see that this line remains level or increases as that test is going on. If it drops, that indicates that the grout is not creating the passivation that we want to see for the steel. It doesn't mean that corrosion is set in. It doesn't mean corrosion is occurring, but it gives us an indication that the grout is not performing like we expect it to perform, and there could be potential in the future for corrosion to start. So we have two different measurements. The first one, we call it C3, and we're checking for, is it fully grouted? We expect to see somewhere in the range of 1.5 to 3 volts in magnitude between the two. And that tells us if it is the well-mixed grout that we're looking for. If it's somewhere outside that range, it could mean that it's not the kind of grout we're looking at. But this also needs to be calibrated for the grout you're using. I'll get into that in a little bit. The second measurement is a C1, C2 passivation of the steel. Like I was saying, we don't want to see it drop off. We want to see it to look basically the same as this graph does, or to increase. Once it drops off, that indicates that the grout is not performing very well. All right, so just kind of give you a diagram of what these measurements are doing. So it's taking a measurement between the inner electrode and the outer electrode. It's doing it for the bottom sensor and the top sensor. At every location, it always needs to have two sensors. The bottom is a reference sensor, while the top is taking the measurement that we really want to look at. And then it's taking a second measurement between the two sensors. So here's a little matrix of different measurements that we can find and what it means. How do we interpret these? So we're going to define our VC1 as the top, and VC2 as the bottom. And the VC1, we compare the results from VC1 to VC2. So VC2 is our reference. VC1 is what we're measuring. So if VC1 is similar to VC2, then we know that the grout level is full. We know the grout is of the same consistency of what we expect, and we have a very high degree of confidence that there's no corrosion that's going to occur on these tendons. If VC1 is lower than VC2, well, this means that the grout level is full, but the quality of the grout, it might have too much water in it. It indicates that there's some kind of bleeding that's happening between the bottom sensor and the top sensor. That bleeding action is causing different results and indicates that there could be a risk of corrosion for this tendon going into the future. Again, it doesn't mean corrosion is occurring, but it means that there's a risk for it because the grout's not performing as we expected it to perform. If VC1 is an open circuit, that means there's nothing that bridges the contact between those two electrodes. But VC2 is normal. So you have a normal VC2 reading, but VC1 is open. That means it's partially filled. It means the grout's somewhere here in the middle. The VC2 sensor is able to detect it. Everything looks good, but VC1 is showing open circuit. So it's partially filled. And if both VC1 and VC2 are open circuits, that means there's no grout, there's nothing that's bridging these electrode connections, and the tendon at that location is completely empty. So anything other than the first scenario indicates that there is potential risk of issues going on in the future with that grout. All right, so in summary, we're taking two main readings in the grouting stage. The first one is at the time of grouting, within about 30 minutes. And what's great about this is if we find that the tendon is not full or if it's partially full at this time, we can actually hook back onto the tendon and continue to inject grout until we get the kind of reading we want to see. So we can actually fix the problem immediately with this instead of coming back a few days, weeks, months later, whatever it is, to come back and fix the problem. And we check for the passivation at about 3 hours. And this is, again, it's going to be very dependent on the kind of grout and needs to be calibrated to the grout that you're using. There's also some potential for this working in the long term for checking the corrosion risk during the life cycle of the bridge. All right, so we're going to get into our pilot project here. Overview of the project. This was in Kemah, Texas. It's just a little bit south of Houston. As far as the post tension is concerned, it had 20 PT caps across the whole project. They are building this basically bypass in downtown Kemah, so cars can drive right through and not have to go through all these nasty stoplights. Each of these bent caps had 4 tendons, 37 strands each. And for the pilot project, 2 of the tendons on bent 107 were converted to PL3. So 2 of these 4 on one side were EITs, and the other 2 were just the normal 37 strand tendons. Here's a elevation view of our PT shop drawings. So we have tendon 1 is the top tendon, tendon 2 is the bottom tendon. We put VC sensors at the anchors and at the high point. We have junction boxes for the wiring at each of the VC sensor locations, and we wired them all down to a main junction box here where we could take our measurements. All this wiring is by no means required, but for the purposes of this pilot project, it made a lot of sense to have a nice central location near the ground level to do all this work from. So we had the VC sensors at the high points, and this is kind of what the internal schematic of the tubing looks like. So tubing for the wires to come out. Same thing at the anchors. So the critical hold points that we had during the process, we did a pre-pour air test after the duct was installed. This helped us check for any kind of leaks in the duct, any issues that we might find that we want to correct before we pour concrete. We checked prior to installing the strands, make sure that there's no contamination that got inside the duct, right? No cement paste or anything like that that could cause electrical leaks for us. We checked prior to stressing and after stressing, making sure that the strand remained isolated between the two. We checked prior to grouting, and we also set up for the vacuum assist grouting. So this is a little bit of a different process than your normal air test. We were doing a vacuum test. And then we checked after grouting for the electrical isolation. And that went ongoing for several months. So how do we mitigate some of our potential leaks? So what we did was apply heat shrink over the duct couplers. We used protective shells, which are these ducts to provide additional separation from the rebar and the duct. We want to make the tendons airtight prior to grouting. And doing that, we were able to eliminate the high point grout vents on the tendon number 2 by doing a vacuum assist grouting. And then we use the VC sensors in lieu of a post-grout inspection to verify that everything was full. And by getting rid of the post-grout inspection, that's one more step of eliminating potential leakage, electrical leakage after the fact. So here's a couple pictures of the actual project itself. You can see the protective shells that we placed between the rebar and the ducts. You can see the tubing coming out of the formwork for later connection to the junction boxes. Here is where our VC sensors were installed at the high points. These are all tilted at an angle, and we'll talk about that here in a minute. So what is really standard in Europe is a requirement to fill the duct up 95%. And the reason for that, at least for the void sensors are concerned, is these sensors only tell you, is it full or is it not full? It doesn't tell you the level, right? So if you have a duct that's 98, 99% full and your void sensor is straight vertical, well, that sensor may not catch it and tell you, well, you have a problem. But really, is 1 or 2% not full a major problem? More than likely, it's not going to cause a big deal, right? So these are located at an angle that correspond with 95% of fullness. So this tells us, is it at least 95% full? And that's a lot more useful than knowing, is it 100% full? So if you're not 95% full, that means you have a pretty significant void that should be taken care of. If you're over 95% full, well, you could still be 100%, but if you're not, it's probably going to be a very minimal issue going in the future. But of course, this could be adjusted to whatever percentage you want to see. So that's what we did here, is measure that out, make sure that line is on our vertical so we know what kind of angle to put these at. Here's some pictures of the isolation plate. So installed this prior to installing the anchor head. This is our void sensor ring, and this held the void sensors. So this acted as a distribution plate between the insulation plate and the anchor head, and held the void sensors in place. So you can see here that void sensor just at about 1 millimeter or 2 shy of the surface of the ring. We want to make sure that it does not make contact with the strand and short circuit the process. Here's a before and after of stressing. So you can see everything's in place here during the stressing. The void sensor ring is in between the isolation plate and the anchor head. After we're done stressing, we have a lead wire that was attached to the anchor head, and this is what our measurements were taken off of when we checked for electrical isolation. So here's us wiring it up. Our junction box, everything is color coded for void sensors and EIT measurements. We have a ground wire all connected in here. You can see the wiring that went back into the concrete and then routed down to this box. Here's our setup at the ground level. So we wanted to make sure we have nice, clean access here, especially with the assortment of measurements we're going to be taking. Of course, with the nature of this being a pilot project, we're going to take a lot more measurements than would typically be required. We want to collect a lot of data during this whole process. So I mentioned before, we've had to calibrate the VC sensors to the grout that we used. So these VC sensors have been used, not in the United States, they've been used elsewhere, and they have different standards for grout. So we want to understand how do the readings behave with the grout that we use here. So we took a couple different samples. We have these graduated cylinders here, some samples of the ducts, couplers. You can see void sensors sticking out, all different sides of it. And we filled up these different specimens with properly mixed grout. So everything below the blue line is the kind of grout you would want to see inside your tendon. Everything above the blue line is what we call bleeding grout. So we mix the grout with 50% more water. This would simulate somebody accidentally dumping more water into their grout mix, which, you know, that's a very plausible thing to happen, and cause that grout to be poorly mixed. And we wanted to see what kind of different readings we get. So these are the results of the two graduated cylinders. So again, we got cylinder A is completely good grout. Cylinder B, we had good grout down here, and we had very wet grout above. And we're taking measurements between the two. So the first graph here is at 30 minutes, then we have 3 hours, and we have 1 day. So what you can see is that graph where it immediately drops off. We do expect this to happen in the first 3 hours. The grout is still very wet. It's highly conductive, just like salt water is more conductive than fresh water. Grout has so many floating particulates in it that it is highly, highly conductive. Which is actually interesting because on the wet grout, it doesn't drop off as much. And that's because the concentration of particulates isn't quite as much, so it's not as electrically conductive as the properly mixed grout. But you can see after the grout's set, after a day, how much more passivation that this has created than the wet grout. The wet grout is still showing a very, not the kind of curve we want to see here. It's showing a drop right there, while this one's actually increasing. So you can see that the results are very black and white in this case. It's very easy to interpret of this was the well-mixed grout versus this is the poorly mixed grout. So looking at the results of our actual tendons. So here we have the two tendons checking for just the electrical isolation. The vertical graph here, the y-axis is our specific resistance. So this is our measurement in ohms times the length of tendons in meters, and that's what we were checking for. X-axis is time. So we expect the resistance to increase over time. In this case, tendon 1A, which is this one right here, met that requirement that we're looking for on this orange line, met it immediately. A little bit unusual for it to be that high so quickly, but that's great. It was very well isolated, continued to increase for the first 7 days, and then increased a little bit from 7 to 28, and basically plateaued since then. Our tendon 2A measurements, we noticed that there was a problem from the get-go. It was quite a bit lower than what we were expecting. It did increase for the first 7 days, and something kind of unusual happened, where it was oscillating up and down, and eventually did meet the threshold, albeit beyond 28 days, but it met the threshold and continued to increase. Now, we didn't go back through and investigate further of where this leakage is occurring. It wasn't really important for the integrity of the structure to understand that. But it gives us an indication of something was going on in there. It could be a very, very minor leak that changes based on the humidity, the shrinkage of the concrete. All those kind of things could have had a very small, have a significant impact on that tendon's electrical isolation. But what we do know from these measurements is if we see that this tendon, say in the future, we were to go back and look at it and we see that the measurements are kind of sporadic, that may not indicate that there's any new development in the tendon. It was sporadic from the beginning. If we see that the tendon 1A drops off in the future, then we would know that there's something that's changed in that structure. Something's happened that's created a leak that might warrant further investigation to go and solve. So here's our void sensor tests. This is tendon 1A. We have 3 locations. We have the east end, the high point, and the west end. And again, we have 30 minutes, 3 hours, and 1 day. The results are all pretty consistent with what we had expected, except for the high point being quite a bit. Everything's showing very high initially, which was, again, a bit unusual, but not really a problem. But the east end and west end were both showing the typical results that we would want to see. So this indicates that the tendon is completely full, that the space between the bottom line and the top line is enough to indicate that it's good grout, and we should be good to go. We don't have any real cause for concern on that tendon. Tendon 2A, similar results. The high point is doing the same behavior, which is consistent. Our east end and west end, we can see that they're more flatlined initially, but even after 1 day, they're either flatlined or increasing, both of which are acceptable results for us. So this again proved to us that the grout was injected completely and of the proper kind of mix that we're looking for. And that concludes my presentation. I don't know if there's any questions, or Wade, I guess I'll give it to you now.
Well, thank you, Jordan. Yeah, this is Craig Freeby, and then I will ask Wade to step in and moderate the Q&A here. We have a few minutes left, so if you had a question and you haven't put it in the chat yet, please go ahead and do so, but I will ask Wade to go ahead and start with Q&A.
Okay, great. Very nice presentation, Jordan. Very interesting technology. I've got a stack of questions here for you.
Wonderful.
So, but we've got a little bit of time, so that's good. First question is, if not properly maintained, could the sensor wiring itself actually be a path for stray currents into the system and potentially cause corrosion?
Yes, it does create a potential path. So that would be something that needs to be maintained in proper conduit. It doesn't make contact with the strands directly, so I don't see it being a main concern. If you do have some kind of high, say it's a high-speed rail structure where you have concerns for stray currents, that would be something that you may want to check and further evaluate. Now, it is also possible, because the VC sensors, their primary purpose is done after 1 day. So you could go back and cut those wires back as short as you can, cap them off, and maybe inject the tube with some grout to make sure that nothing ever happens in the future. So there's some things you can do. It just depends on what you want them to use them for and how you maintain them.
Okay, great. Just looking holistically at the system for electrically isolated tendons, has there been enough applications of the technology that y'all have determined kind of the typical, I'll call them hot spots, but typical spots for failure of the electrical isolation and what's most common, both maybe initially during installation and then over the long term as the tendon goes through its service life?
So talking with talking with our experts in VSL International, the way it was explained to me is you can never expect 100% success with EIT. Typically, the way the contracts are written, that's because, you know, any slightest mistake in the workmanship can break that isolation. And the 100% success rate is just not a realistic expectation. So the way the contracts are typically written is there's a minimum threshold. Say it's 90% or 95% of tendons need to meet this isolation, or there's some sort of penalty. So that's an incentive for, right, to maintain quality control. And typically, a project will start out and they may have 70, 80, 85% success rate. But then as the project goes on, as the crew becomes more familiar with how to install it, that success rate will increase over time to hopefully average out to be at least 90%. And again, kind of what I was trying to make clear is the electrical isolation, just because it's not isolated, doesn't mean that corrosion is occurring or that there is any real risk for corrosion. What it really does is allow you to monitor it. So if you can monitor 90% of the tendons in your bridge, that's going to give you a really good indication. You know, if you start to see that the isolation breaking in a lot of tendons, it's going to give you a good indication of something's going on and that you can go in and mitigate that. And the most common places that was hammered at me during this project from our guys is to make sure the duct connections are completely airtight. It seems that if there's any kind of cement paste or grout that can get through that duct coupler, that's going to break the isolation, and it's very, very challenging. It's really impossible to fix after the fact.
Okay, good. Here's the $1 million question, maybe literally. As far as the efforts it takes and the equipment and things to put together an EIT type of a system, and perhaps the VC sensors as well, how does that affect the overall installed cost of the PT system?
The overall cost of the PT system, I would ballpark somewhere between 30 to 50% more, but the overall cost for the bridge itself is going to be very minimal. You know, a lot of times, for example, just using, you know, this project, SH146, I don't know how much it cost to build the 5 miles of bridge that they had there, or just call it the 2 miles of bridge where the PT was. But I'm sure it was millions and millions of dollars versus, you know, a couple $100,000 for the PT. So overall for the PT system, yes, it's substantial, but the cost for the bridge is pretty minimal in the grand scheme of things.
Okay, good. Have there been any applications with precast segmental bridges, and were those applications, do they use the segmental duct couplers?
I do know that there is. You're gonna have to forgive me because I don't know the names of the bridge, but I do know that there's one ongoing in the UK right now that's using segmental duct couplers with EIT, and I believe void sensor also. But I know it's ongoing, and it's been, from what I understand, they've had success with it.
Yeah, I think it's probably that high-speed rail 2 project, right?
It might be.
Yeah.
Yeah.
So a kind of a follow-on question to that, has there been any testing to determine whether an epoxied precast segment joint might provide enough electrical isolation to be able to be used in an EIT application?
I know epoxy is one of the remedies. You know, say you have some kind of penetration through the duct, using like an epoxy sleeve is one of the repair methods for it. So I would guess that the segment epoxy creates a nice isolation for the tendon. The problem is if you have any kind of contact between the strand and the concrete itself, or the grout makes contact with the concrete, you're going to see a break in isolation. Now, it's not going to be a complete drop of isolation, but you will see it impacted. And if you have that across many joints, and every joint has a small leak, it can add up to, you know, to not having your isolation that you're looking for. So it's really best to have a
Yeah.
complete isolated system, so that if anything happens in the future, you're able to pinpoint that issue. Because if every joint has a small leak, it's going to become very challenging to identify the problem leaks versus the minor leaks.
Yeah, interesting. Okay, yeah, it would be hard to isolate that grout from the concrete if you had a potentially if you had an epoxy connection there. Interesting.
Right. Yeah.
Here's another question for you. So it looked like there was some kind of a handheld sensor that was used to determine the resistance along the length of the tendon. Is that correct? You had a picture of some kind of a handheld instrument.
Yes, so there was that wasn't an instrument that we used on this project. That was more of a sample instrument. So that's an instrument that's able to detect the frequency coming off of the strand when you apply an AC current, and that's the type of equipment that you would use to find the leakage, and that would work well with segmental bridges on like a PT deck where the strands are only a couple inches from the surface of the concrete. If you're talking about a bent cap structure like ours, where it's several feet down into the concrete, you're going to have a very tough time, I think, locating that. So there's certain applications where that's going to be beneficial to use. Does that answer the question?
Yeah, no, and that really was the question, was kind of what was the max effective depth for that type of a handheld sensor system. So
Yeah, I couldn't tell you. I don't know enough about them, what the max effective depth, but I know it's going to be a lot more effective for, a couple inches of concrete versus a couple of feet.
Okay. And then there's a question about the way to monitor the system. Is there a way to set up like a remote monitoring system that perhaps communicates back to a central location somewhere?
Yep, there's technology that VSL has done on multiple projects that has that remote capability, and it monitors. I think it's every couple of hours it takes a reading and records, or it might be a daily reading. But obviously it requires power to the structure at that location, right? But there is a system set up that can be implemented to do that, and it could alert you to whatever kind of breaks in isolation that you have throughout the life of the structure.
Okay. All right, good deal. Yeah, because some of those instrument boxes and junction boxes and things you were showing at SH146 look like they might be at a spot that might be vulnerable to vandals or something. So if there was a way to put those boxes out of reach and then remote tie into them, that might be
oh yeah,
that'd
be ideal. That'd be ideal. Yeah, I mean, I'm not going to say everything we did on the pilot project is what you would want to do in a production, but for the purposes of what we're trying to accomplish, it met our needs.
Great. Okay. Yeah, just a couple more questions.
Oh, you got more? Okay.
Yeah, just a couple more. So the VC sensor, is there and this is sort of a weird case, but if the grout came up and sort of dipped the sensor in grout and then later drained away, would the VC sensor be able to see that, or would that change the readings, or would that give you a false sense of security that grout is present?
That's a great question. I would have to consult with our team at VSL International to figure out what kind of data they have on that.
Okay, great. And then the last question, what owner agencies in the US have expressed an interest in implementing EIT tendon systems in the near future?
That would be a great question for the FHWA. I don't personally know of any particular owner. I'm just not in those kind of conversations. I do know that there is an interest by several agencies to improve post-tensioning in general. FDOT is a big component of that. They've been doing things like flexible filler and things like that to try and improve what they're doing. So I know there's definitely a push by some agencies to improve, whether it's specifically EIT or not. I'm just not privy to those conversations to know.
Yeah. Okay.
Yeah, so
10-4.
I guess I can sort of add a little to that. I know, so this project was the second demonstration of the electrically isolated tendon technology. There was a splice girder bridge done in Pennsylvania in 2019, I think it was, that used EIT. I had understood they were looking at a project also, they being Federal Highway, looking at a project in California to do another demonstration. And I will put it up here in the questions pane or in the chat pane, a link to a Federal Highway tech brief on electrically isolated tendons. And so they're certainly encouraging use, whether or not the technology is still at a, I'll say, demonstration phase, and whether an owner could get some compensation for the delta cost. That certainly would be, an interesting thing. And then the other thing that seems to come up on this is people have asked, well, where would I use this, right? Because, do you do every single tendon and every bridge, and, the associated cost? And so that sort of ties back to the webinar that we did back in May of last year in 2022 about a methodology for risk assessment of post-tension tendons. That kind of walks you into, whether or not it, an electrically isolated system would be warranted for, for your particular application. And of course, if you think about it, you're not likely to use this for transverse deck post-tensioning tendons, but main load carrying members like post-tension bent caps, that's certainly a location where you start to think about using that technology. And, is the extra expense warranted is always, the question, or maybe you do isolated ones, only the ones, the bents that are underneath open joints where you would have an increased corrosion potential. That would be where it would be useful. But so there are some resources out there to kind of help people decide when and where to use them. From my perspective and what I've seen, there are a number of post-tensioning suppliers who have these systems available that meet Buy America. So it's really ready to go. It's just a matter of sort of working out some of the details in terms of where you use it, and then, as you all were just talking, what is your long-term monitoring system need to look like, right? And in fact, I was part of the team that went to Europe and looked at this, and there's at least one owner, they're not even monitoring the tendons long-term. They felt like they got the information they needed in terms of the encapsulation, that they had got good encapsulation of the tendons, and they're not even bothering to take routine readings. The equipment's still there where they could actually go in and take readings. They're just not using it because they have that much confidence in what they got back from the initial readings.
Yeah, I was going to add to that too. So there's two big benefits. One is, of course, the monitoring, but the second is to prove the isolation, you have to have a very high degree of quality control on the project. Right. That's usually the downfall of the problems that we found, is that there's poor quality control on certain projects, and it's caused issues 10, 20 years down the road. So if you have a very high degree of confidence that this was done well, because you have actual data to look at to say, yes, this is all isolated, it gives you great confidence that you're not going to have any problems in the future.
Yep. All right.
Well, those were all the questions, Greg.
Okay.
Jordan, thank you so much. It was a great presentation. So, Greg, I'll hand it off to you.
All right. Well, thank you. We're a little bit past the hour, so I appreciate everybody hanging with us. Again, you will, as a registrant, you'll get a link to the recording and the slides. If Jordan will let us put up a PDF copy, and then also your attendance certificate should come in about a week. So with that, we will close the webinar, and I will say thank you, everybody. Thank you, Jordan. Great presentation.
All right. Thank you.